All right, perfect. It just dinged after all that time. Okay, so last time we were calculating volumes, right, of three-dimensional shapes, and we did it for cross sections of things. Okay. So the cross section could be any particular shape, but they usually do easy geometric shapes so we can calculate the area of those cross sections, right? So when we started off, we did it off like, I think we started off with a very simple square, right? So if you found the length of one of the, between the two functions as the length of your square, right, or the side of your square, then to get the area of that square, you just take it and you square it, right? So you have to calculate this length right here that I'm kind of showing with my mouse right here, right? And it was just top function minus bottom function to get that distance. And once you got that distance, that got you the side of whatever it is that you're talking about. So square was the first thing we talked about. Then we talked about a semicircle, right? So that ended up being that if that was a semicircle, right, that means that the length here was no longer a side, but in this particular case, it was the diameter, right? It was the diameter. So we had to divide that by 2 to get the radius because the area of a circle is pi r squared, and to make it a semicircle, we just took half of that. That's where that comes into play, right? So your job is to, for these cross-section problems, is to find that area, right? Find that area of that particular cross-section, whether it be a rectangle, circle, square, or the last problem we did, which was a triangle, right? But it wasn't just a regular triangle, it was a equilateral triangle. And we showed that an equilateral triangle, to get that height, took a little bit more work, right? It took a little bit more work. It required us to look at the 30, 60, 90 triangle. And then, of course, I said, you know, most students in AP Calc don't bother deriving this anymore, right? And they just end up memorizing instead. So the equation to calculate the area of an equilateral triangle is just broken down by this right here, which is if you know the base of your equilateral triangle, you square it, and then you multiply by the square root of 3 over 4. But we proved that. We showed that that is the case when we worked it through and saw like, hey, if the base is this length here, half the base times the square root of 3 is the ratio to find the height of an equilateral triangle. That's what we were able to do. Okay. Then I think I ended the class with like 2 more special triangles, right? There was an isosceles right triangle where the leg is the base, and if you have trouble seeing that where the leg is the base, it looks something kind of like this here. If I had this real quick drawing right here, let's say I had this like so, right? This is my XY on the 2-dimensional plane right here, and I'm gonna have something popping out of this thing. If I have a isosceles right triangle with the leg as a base, right, like so, and if it's an isosceles right triangle means that the 2 legs are perpendicular to each other. So it looks something like this. Sorry about this. Can you guys see that okay? So if it's an isosceles right triangle, this leg right here is equal to this leg right there, and the hypotenuse is going diagonally that way, right? That's what an isosceles right triangle looks like with the leg as its base. If you do it with an isosceles right triangle as the hypotenuse as its base, it looks somewhat, it has the same idea of it being the legs being equal to each other, but the hypotenuse is the one that's going across, right? So if you have it going like this, like so, it kind of goes this way, like that, and you have the right angle here, where this side and this side are equal to each other. So the length from here to here is actually equal to the hypotenuse. And to get this right here, right, it would just be that right there. It would just be that. There's a breakdown of that as well, because the height of this thing, right, you could go that way, or you could try to calculate what the sides are and then do 1/2 base times height of that. But yeah, that's that one right there. So you could just memorize this right here if you know that it's an isosceles right triangle with the hypotenuse as the base, or an isosceles right triangle with the leg as a base. Those are your 2 equations right there. And of course, equilateral triangles. Sometimes they don't do any of those. Sometimes they do just like a triangle with a right triangle as your cross section with the base equaling to that side, and they tell you the height is a ratio of that. So there's a lot of things that you got to keep in mind when you do these types of problems. And your ultimate goal is basically to find out the area of that cross section. And then once you find out what the area of that cross section is, you take the integral of it from A to B. And that's it. That's all you have to do to calculate those volumes, okay? Yeah, that's pretty much it. So a lot of these problems, it's going to come down to your geometry skills of figuring out the area of that particular cross section, and maybe a little bit of algebra skills to calculate what the base is of that cross section. Right. So let's start off with this problem right here. This one's a different one right here, where they don't give us an equation, but they give us a description of the base here. So we're asked to find the volume of a solid whose base is a circle centered at the origin with a radius 3 units, whose cross sections are described. And we'll do an easy one. We'll do an easy one first. Let's go with the cross section that are described. Let's go with the first cross section. The cross section are perpendicular to the x-axis. Are, let's say there's just squares, just to keep it easy for today, right? Let's say they are squares. Okay. So first things first, I don't even have an equation of f of x, right? I don't have an equation of f of x. I don't know what this looks like. They just tell us that the base of this thing is a circle centered at the origin with radius 3 units. So I know what it looks like, right? I know what it looks like. So here's my my circle. That's terrible. Knock me into this. Terrible. Just there's my circle. Not bad, right? Not bad. That's a little bit better, right? And they're telling us that it has a radius of 3. 1, 2, 3. Okay. So, I need to create a thing. I need to find the volume where the cross sections of this thing is going to go from up here all the way to here, right? And it's going to make a square out of that. It's going to make a square out of that. My only issue is they didn't give us any equations. They didn't give us any equations. I just know that if I'm looking for this volume right here, right, that I have in red right there, that volume is going to equal to the integral. Now, maybe you guys can tell me this. What is it? What is my a and my b value? What is it to go from here all the way across to here? What would that be? Well, they tell us it's radius 3, so it needs to go over here to 3. So I need to go, I know that my integral is going to go up to 3. And Monica, you got the right idea. It is the diameter of 6, but if I'm looking at it in terms of my integral, right, I need to do the integral from what to 3 to make that crossover to 6 here. What's this value over here? What's my a value right there? It's going to be -3. That's right. So the integral is not that hard to set up, right? The idea is we're going to do the integral from -3 to 3, and I just need to find out now what is the area, right, of my cross section, which is a square, right? Which is the square, which isn't too bad, right? To calculate that area, right? I know that this area is going to be a square, so I just need to know what the side is equal to, what this thing in red is equal to, and I just need to square it. But I don't know how to. I don't know what that is. I don't have any equations. Anyone have any ideas? Anyone know what an equation of a circle looks like? Anyone ever been shown that before? What's an equation of a circle look like? Have you ever seen something like that? Pi r squared is the area of a circle, but that's not what this question is asking for, right? That's not what this question is asking for. If we think about it, right? If we think about this, oh God, okay, I apologize now because my drawings are never that good with 3D stuff, but so here's the thing. I'm not looking for the area of that circle. I'm looking for the area of this square that pops out of that said circle, right? I'm looking for this area right here. But in order for me to do that, right, I need to get that length. And it's not pi r squared, not pi r squared, but David's saying something like y minus x plus y minus x equals to r squared. That's pretty darn close, pretty darn close. And David's going with this one right here, x minus h squared plus y minus k squared equals to radius squared. So the reason why I'm bringing this up, right? We know that the area of this cross-sectional square is supposed to be whatever this length is squared, right? That's how that one is. But to get this length, I need to know what this function is from here to here. They don't tell us that function. And David's written out a overall form of a equation of a circle, right? Not the area of the circle, the equation of this that draws the circle, right? The equation that draws the circle on your coordinate plane. To draw this circle right here, the equation is supposed to be, and he's writing out like this, y minus h squared plus, I'm sorry, that's clearly an x, x minus h squared plus y minus k squared equals to r squared. This is the equation for a circle that you're supposed to know coming into calculus. I know that sounds ridiculous. There's a lot of calculus, there's a lot of things where it's just like, you're supposed to know this stuff from before. And I think that's what makes calculus pretty difficult. It's the fact that everything that you learned in the past, you need to be able to recall on it. And if you weren't taught this before, they're kind of like, well, you need to know it for this class. So if you didn't know that, this is an equation for a circle where h and k would be the center of your said circle and r is the radius of your circle. So right now, since my center is here at the origin, my h and my k would be 0. So I would write this out. This equation here would be x squared plus y squared. And this is going to equal to my radius squared. In this particular case, it's equal to 9. It's equal to 9. Right? Now, to get what this value is up here, I need to get this in terms of y equals to, right? So I need to do a little bit of algebra and solve this algebraically for y. So if I move the x squared over, I end up with y squared is equal to 9 minus x squared. And then to get rid of the squared on the y right there, I just have to take the square root of both sides. So I end up with y is equal to, now this is the part that you got to pay attention to. When you square root something that's squared, you get plus or minus, right? Plus or minus the square root of 9 minus x squared. So check this out. What we've essentially done is found my function without them giving it to me. They just gave me a description of it. And this top part right here, this right here, that is going to be y is equal to the positive square root of 9 minus x squared, whereas this one down here is going to equal to y is equal to negative the square root of 9 minus x squared. That's it. That's how we're going to find that distance, right? The top function in this case is the positive version of that square root. The bottom function of this thing is the negative version of that square root. And that's how we're going to find this distance, right? That distance right there, this distance in red, right? From here all the way to here, to get this distance, all I need to do is the square root of 9 minus x squared minus the square root of 9 minus x squared. Negative. Almost forgot that, right? Negative. So what does that become, by the way? I have here the square root of 9 minus x squared minus negative the square root of 9 minus x squared. If you simplify that out, those negatives become a positive. This is going to simplify to 2 times the square root of 9 minus x squared. So what's the distance in here that's in red right here from here to here? It's equal to 2 times the square root of 9 minus x squared. Meaning, if I'm looking to calculate the area of this right here, this square right there, to calculate that area, that's going to be equal to 2 times the square root of 9 minus x squared, what? Squared. And that's it. That's your setup. Once you get that down and you figure out what the area equation is, then you just go back and say, oh yeah, what was I trying to find? I was trying to find this volume. Well, knock me. We know that the volume is just equal to the integral from -3 to 3 of the area function. And that area function in this particular case is going to be 2 times the square root of 9 minus x squared dx. Then it becomes a integral problem, right? That's all it becomes. It becomes this integral problem. You can square this, by the way. It is this whole thing squared. So this volume right here is going to be equal to the integral from -3 to 3 of 4 times 9 minus x squared, because the squared with the 2 makes that a 4. The square with the square root cancel out. There's no plus signs in between the 2 and the square root. So I can just multiply that together. And if you want to simplify this even further before you do the integral, right? Before you do the integral, you can write this as, take that 4 out in front so you have less things to worry, or you could distribute it if you want. I'm going to just, no, I'm going to put it I'm going to put it in front of the integral of -3 to 3 of 9 minus x squared dx, which makes it a little bit easier to deal with, right? And then I just do my integral here. This is going to be equal to 4 times the integral of 9 is going to be 9x. The integral of x squared is going to be x cubed over 3. This thing is, of course, being evaluated from -3 to 3. And you plug in those values and you evaluate it out and see what you get. I think it comes out to like 100 something. You know what, Nakmi? Just show the work. Why are you being lazy? I don't know, Nakmi. All right, let's plug this in. So we got here 9 times 3 minus 3 cubed over 3 minus 9 times -3 minus -3 cubed over 3. And of course, this is all being multiplied by 4 out front right there. So volume is going to equal to 4 times, let's do this real quick. 9 times 3 is 27 minus 3 cubed is 27 divided by 3 is going to be 9. That's what this one's going to be equal to, minus -27. This will be minus, this will become a plus 9, I believe, right? If I look at that correctly. -27 divided by 3 is going to be -9. Minus -9 becomes a positive 9. Finish off this volume 4 is going to equal to 27 minus 9, which is going to give me 18. Minus a -18, so that's going to be a plus 18, I believe. Right? Is that right? -27 plus 9 is going to be -18. With a negative there, it becomes plus 18. So you end up with the volume is equal to 4 times 36. 4 times 36, volume in this case is 144. 144. So again, the integral stuff is just stuff we've done in the last chapter. It's not that crazy. This looks complicated, but we know how to evaluate an integral that has numbers there, right? We also know how to do that on the calculator as well. This isn't that bad. What makes it annoying is getting to the point where you have to find the function that you're taking the integral of, right? So if they give you like functions, like in this case, they gave us functions here and we could draw it out and we can see what the base is. You can clearly see how to find this distance by subtracting, the top function minus the bottom function. If they don't give you a function, they give it to you in a sneaky way. You need to be able to think and figure this out. And I think what most students will probably struggle on is like, you might not know some of these equations by heart. So for the circle equation, I don't know how you could derive it, but you kind of have to kind of know that this right here is an equation for the circle. And I'm just hoping that on the test, I don't think they'll do this. I think they'll actually give you the functions for the base. So I just wanted to show you that just in case you don't see a function there, but you know what you're supposed to do. Then chances are it's supposed to be some function that you should know of. And if that's the case, I'm hoping that me exposing you to the circle one will help you out for that one particular problem. Okay, hopefully, I'm hoping. But yeah, that's that right there. So, yeah, get that down. Get some of these area equations down. It's not like the SAT where they give you like the page where you have the equations for all the areas and all the volumes. You kind of are expected to know them. So, yeah, hopefully, you have a little bit of exposure to it, so you'll be able to see like an idea of what you should do to get there. Okay. All right. That's pretty much it for volumes using cross sections. It's pretty like straightforward. Get the area of that cross section that you have, and then just do the integral from A to B, wherever it starts to wherever it ends, and you got yourself your volume. Have you guys been practice? You know what? I should have given you this site. I showed you guys that site that shows you a nice visualization of the cross section, right? I think I showed you guys this site. This one right here. Hello, there we go. This one right here, right? Did I show you guys this site? Yeah, I think I did, right? Let's just assume that I did. So on this site, you can click and drag this right here to see it in 3 dimensions. Hopefully your hands aren't as shaky as mine. And then you can move the A value to wherever you need it to be. In this case, it should have been here, it looks like, right? And then on the right-hand side, they have basic shapes. Oh, you're saying yes and yes. Awesome. So yeah, they have basic shapes here. Like you can have a square, and you can kind of see what that's supposed to look like along the way. And they even draw this line right here for you. They don't do the calculations for you, but they do the lines right here. So let's go ahead and key in the functions that we just had right here. Let's see, it's the square root of 9 minus x squared. By the way, if you don't know how to type these things, you like, how did I know square root is SQTR? I don't know how to describe that, but that's the easiest way to type in square root right there. Actually, what happens if I? Oh, that's just the symbols. Yeah, I don't. You kind of just have to. Oh God, let's go over here. Hello. There we go. Okay, so negative square root 9 minus x squared. There we go. That right there is the circle, and we need to move this over here, so it goes from -3 to 3, like that. And there you go. You can kind of see it now. It's like that. That's what it should look like. If you want to see it with the solid, click on the solid and increase the number of squares, and you can see what this shape should look like if it was all smooth and you had infinitely many squares. Because when you're doing the integral of it, the number of squares is actually infinity, not 50. So you kind of see it should all be smooth right there. And yes, that's what I was going to do. I forgot. I was going to give you this link so you guys can play with this and try this out. It doesn't do the calculations for you, but it gives you a nice visualization of it. And like I said, they have a couple of the shapes right here. They have the circle right there. If you want to do it as a circle, right? Like so. They even have a semicircle to go across. But the only one they have is the equilateral triangle. They don't have any of the other triangles. But kind of neat to see. Kind of neat to see the different things that can be made based off of this. Okay, so that's volume using cross sections. I think that's one of the easier ones to be able to visualize, because when they do these types of problems, the cross sections are always going to be some kind of geometric shape that you can imagine, right? Square, rectangle, semicircle, circle, triangles, all those stuffs right there. Yeah, I suggest you try to play with it. It's kind of fun to play with, especially when you get to this one, the 3D part. If you click on hold it and then spin it a little bit, yeah, there you go. You can get it to rotate on its own. And it looks kind of cool. I like it anyways. But anyways, that's that. So hopefully you guys play with that. All right, let's start off on the, I believe this will be the last section. I think, well, it's a two-part last section. Hopefully I can get through it all today. Chances are no, but I'm gonna try. Yeah, I'm gonna try. So let's go. Last one right here. Let's go ahead. Call this volume with disk method. Volume with disk method. The disk method is the volume that's created when you spin your function around a particular thing, creating a disk. And you'll say, what? So picture, if you could, right, a linear function. Picture, if you could, a linear function. Can you picture it? Let's say this linear function starts right here at A and finishes right here at B. So here's this linear function going from A to B, right? It makes this kind of like rectangle shape right here, right? Now, if I took this thing and I only looked at a piece of it, let's say I looked at a very small piece of that linear piece, like right here, very, very small piece, right? Like it looks kind of big still, but could you imagine that line is like so small that you're looking at it through a microscope, right? It's a very, 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 very small cut of this blue line right there. Now, what the disk method says right here is you can take this thing, this small piece that I've cut right here, from here to here, you take this thing and you revolve it around something. And I'm going to revolve it around this x-axis for right now. If I took this and I spun this around like so, can you guys picture this? This is terrible. My drawing is god-awful. Let me try this again. So this distance here, I would spin it down like this, and it would come back up like that. This one spins down like this. It comes up like that, like so. Can you guys picture that right there? It's like a disc. Can you guys see it? Oh God, that's terrible. Knock me. Can you guys kind of see it? Right there is it's like a slightly three-dimensional disc that gets formed by spinning this thing around the x-axis. Right? This disk method, right, is the idea that we spin this little chunk around here, and you can see, if you looked at this face on, it's like a circle, right? It's like a circle. Yeah, it's a vertical petri dish. Yeah, that's right. That's right. If you looked at it head on, right, it's like a circle with like a little bit of thickness to it, right? And what you do is, right, you do this infinitely many times from the beginning of this part all the way to the end, and you end up with this shape. And you can kind of see it. It makes a cylinder, right? It makes a cylinder, a three-dimensional shape, a three-dimensional figure. And to calculate this thing, right, is the same idea. We just like the cross sections that we did earlier. This is a cross section of a circle, right, with radius of whatever your function is, right? This radius is going to go from here to whatever that function is, right there and right there, right? Now, to calculate this volume is the same idea as with us calculating the volume using the cross sections earlier, except now these cross sections are all going to be circles with varying radius, right? So this right here is going to equal to the integral from a to b, right? And then we just need to calculate the area of the circle, and the area of the circle, right, is equal to pi r squared. And r, of course, is going to be whatever your function height is, whatever your function height is. Okay? So that looks like this right here. That looks like this right here. So let me show you the screenshot right here. This will be a little bit easier. Boom. R of x is the radius as a function of whatever x is, right? So if you have a curve that's going through like this, we can rotate this thing, multiply it by pi, right? So this right here, that's actually pi. No, knock me. Come on, man. Right here. So to get this volume, right, is going to equal to pi r squared dx. But r is a function of whatever that is right there. So they write it as r of x. But that's the idea of it. Whatever that function is, we square it and then multiply by pi, and that's going to give us the area of this circle. And then when we do the integral of this, we're adding up infinitely many circles, right? If we do this circle here, plus this circle here, plus this circle here, plus this circle here, and you just kind of add it all up, you get this three-dimensional shape, this three-dimensional cone, right? Or cylinder, or whatever it is that you're dealing with. We call this the disk method because each of those circles, if you can picture it, is just a disk. And then we're adding up infinitely many disks along the way. Okay? We're adding up infinitely many disks along the way. So if you think about it, it's not that much different from the cross-section ones, right? But it's just the fact that it's not popping out of the base, right? Like this right here is your base. It's not popping out of your screen like the other ones are. Instead, it's being spun around in a circle, right? It's being spun around in a circle. And that's what it looks like on this chart right here. If I take this off of this one right here, where's my mouse? Hello? There you are. I take it off that equilateral triangle and put a circle here instead. That's the idea that you kind of looking at. See that? So you're taking it and you're kind of spinning it around that, right? You're spinning it around that. Okay? So let's go ahead and take a look at this one right here. And here's what I want you to try. Here's what I want you to try. Let's take a look at this function right here, this example. Like so. And I want you to, at this very moment, take a look at this problem. I give you some functions right here. And I want you to use the website I gave you right now to see if you can sketch what it would look like to go from 0 to pi. From 0 to pi. and then see what it would look like rotating it around the x-axis. So I'm going to give you about, let's go 5 minutes. I'm going to ask you to graph it using that website that I have in the chat right there, and then see if you can select the circle feature and see what that would look like. So I'm going to give you like about 3 minutes. I'll be right back in about 3 minutes. So go ahead and try this out right now. Try this problem out. I want to see you guys give this one a shot. I'll be right back. All right, how'd you guys do? Were you guys able to draw it out? Were you guys able to type in the function that's in there and see what it would look like? Let's see, we're dealing with f of x is equal to the square root of sine of x, right? That's not something that most people just know based off, like, right off the top of their heads. I don't know what it is off the top of my head, but I do know that we're looking at it from 0 to pi, right? From 0 to pi. So if you were to graph this, right, and you didn't have like GeoGebra or something, and you just had your TI calculator, right, just take a look and see what it would look like. So y is equal to second square root sine of x. We'll go ahead and take a look at this graph. Man, that looks kind of weird. So let's go ahead and zoom in a little bit here. Let's go ahead and adjust this window. Let's go from -1 up until 3, because that's where pi is. Right, and we're going. Actually, we're going to go a little bit past that. So let's go up to like 5, let's say. And the y values, of course, are probably going from like -1 up to like +1. I'm gonna put that as a 2, and this is what it looks like. Oh, that's interesting. So it's cutting off on some of the parts right there. Oh God, am I misreading my notes here? I think I'm misreading my notes. I don't think there should be a square root there. Yeesh. Were you guys able to put it in with the square root? Did it look okay on yours? Mine's is cutting off kind of weird around pi there. Let's give it a try. All right, so let's see here. Let's scroll up here. Yo, why are you? Hello? Why can't I change this? There we go. Okay, let's go ahead with the square root of sine of x. All right, and then this one right here. Oh. Let's go from this one right here. Let's go to that equals to 0, so it goes across the ground right there. There we go. Okay, and we're going to look at it from here to here. There we go. You guys see that okay, or does that look all right? Hopefully that does. Okay, so it's this right here, this little like half circle. It's not really a half circle, but it's like a weird looking thing, and it goes all the way up to pi, I should say. There we go. All right. And there we go. Okay. And so it looks something like this. It's being rotated around as a circle instead, right? As a circle instead. So it's, can you guys see that okay? Or were you guys able to draw that out? Let me know. You have any issues doing this or doing the visualization of this? Well, I'm having trouble like fitting it all in there. But yeah. Okay. So it looks something like this, right? The function goes from 0 all the way to pi, right? So to calculate this thing right here, I need to take this little piece right here. Let's do this right here. This little piece right here, let's pretend I zoomed in and I drew this little line right here. And I need to calculate this area right here, right? You see that? That's the disk right there that gets formed. And if you go across over here where it's a little bit shorter radius, that disk is going to be like that right there. So it's a little bit smaller circle because it's dependent on the radius that's there, right? So can somebody tell me, what is this radius equal to? This radius in blue right here. What is this radius equal to? Based off of the function that I have drawn right here, right? Hopefully you guys can see that. That f of x is this black line right here. So that means the radius is just equal to whatever f of x equals to. That's right, Monica. And this f of x is going to be equal to the square root of sine of x, right? That's what we defined f of x as. So the radius is going to be equal to that as well. So if I'm looking for the area of this little circle that I have right here, that area, right, is going to equal to pi, and then whatever r is squared, right? But r in this case is that crazy looking square root, so the area is going to equal to pi times the square root of sine of x squared. So to calculate the volume of this thing, to calculate the volume of this in this problem, it's still going to be the integral type of thing, right? We're doing the integral from 0 to pi in this particular case, 0 to pi, right? Of pi r squared. But r squared in this particular case is sine, the square root of sine x squared dx. And that's it. That's all you have to do to calculate this volume using the disk method. If you think about it, the disk method, like I said, is still just a cross section, but each of the cross sections are always going to be circles, right? And it just gets its own special name that it's like, hey, call it a disk because it makes a disk. To calculate this real quick, let's go ahead and simplify this. I'm going to take the pi and put it out in front because it's a coefficient. This is going to go from 0 to pi, of course, of the square root of sine squared, I hope you guys see that the square root and the squares are going to cancel out. I'm left with just sine of x dx. And sine of x dx, the integral of sine, does everybody know what the integral of sine is? What's the integral of sine, everybody? What's the integral of sine? What's the antiderivative of sine? Negative cosine. Good job. That's what I was hoping to see. The derivative of sine is cosine. The antiderivative of sine is negative cosine. Good. This, of course, is being evaluated from 0 to pi. And we just go ahead and plug that in. So this is going to be pi times negative cosine of pi minus negative cosine of 0. Right? Cosine of pi, I believe, is cosine of pi is -1, isn't it? Right? I think so. So we have here pi times -1. This becomes plus cosine of 0. Cosine of 0 is 1. I believe. Yeah, I believe. So we have here the volume is going to equal to pi times 1 plus 1, which is 2. In other words, the volume for this shape that we have right here is equal to 2 pi. And there you go. That's it. That's it. That's the disk method in a nutshell, right? That's the disk method in a nutshell. Calculating what the radius is, and then realizing that that's just the radius of your circle. And then to calculate the area of that circle, you take it, square it, multiply it by pi, and then do the integral of it. And then do the integral of it. Right? Here, let's do another one. Let's do another one. This one is going to be a little bit different now. We're going to do it, and we're going to, for these problems, will there be calculator problems? Yeah, there will be, and it's the functions are just going to be a little bit more complicated. So when you do the integrals, you just do the integrals using your calculator. The setup for it is still algebraically the same. Like if the function, Monica asked the question, I don't know if I stated it, but if you guys can see it, for these problems, will there be calculator problems? And there will be. And on the calculator problems, they're actually easier to do. Believe me or not. The functions they give you, you just kind of have to graph them and see where they lie. And you kind of get this idea that, like, okay, I'm just looking for the radius of this thing. And then I'm going to apply the area formula to it. So I'm just going to square that function, multiply it by pi, and then do the integral on whatever intervals I need. And then you just let the calculator do that part for you. So, you do, like, it could be some crazy looking function, but it still follows the same concept here. So just to make one up, let's say I went over here and I have this integral I'm trying to find, right? So for this integral right here, let's say it was going from 0 to pi in this case, right? But the function was something crazier that I don't know how to calculate the integral for, but my calculator should be able to. I just have to make sure that I do the right formula. So the formula would be pi times whatever my function is. Like my function could be like something crazy. Let's say it's like e to the, let's say it was e to the x times cosine of x. I don't know what the integral of that is, right? But that right there needs to get squared, right? Because that's my f of x, and then it's being multiplied by pi, right? And I just let this thing do the integral for me, so I'll have it calculated for me, and it'll give me my answer, right? Same kind of concept. It's just the idea that the functions on the calculator sections will be the ones that you can't do the integrals by hand. That's all it is. That's how it's going to show up on the exam. Okay, so that's that one right there. Now, let's take a look at another problem where this is nice because this right here, this disk method is being rotated around the x-axis. This is the key word right here, right? It's bounded by this right here and the x-axis, and it's being rotated about the x-axis. So I'm spinning it around this axis right here. What happens if it's being spun around the y-axis instead? Right? What if it's being spun around the y-axis instead? And that's the next example I wanted to show you guys right here. Let's say I have this problem right here, and instead of it being spun around the x-axis, it's going to be spun around the y-axis instead. go ahead and make that a little bit bigger so you guys can copy this down right here. So integrating with respect to y, two integral case, find the volume of the solid formed being by revolving the region bounded by the graphs, and there's 4 graphs there, and they're being rotated about the y-axis instead. So remember, when you do this stuff, when you do it with the y-axis, it's the same concept, right? You have it as a function of y now, and you need to pay attention to where it needs to go on the y-axis, right? So up here, you kind of see it. You do the integral from 0 to pi because that's what it is when you're doing it in terms of x. It's going along the x-axis. When we're doing it in terms of y, it's just going to go along the y-axis, and you need to see where it starts and where it finishes. So let's take a look at these graphs right here. We have y is equal to x squared plus 1, y is equal to 0, x is equal to 0, and x is equal to 1. So let's graph this real quick. Okay, let's graph this right here. So I'm going to go ahead over here and sketch a graph of this. So the real easy ones right here, like y is equal to 0. OneNote is crashing on me again. Y is equal to 0, right? That's this one. Let's do this one in purple right here. Y is equal to 0. That's just going across the x-axis like so. That's this right here. Right? That's y equals to 0. X is equal to 0. That's just going across this x-axis right here like so. Right? That's what x equals to 0 looks like. Right? And then we have 2 more graphs here. One is going to be x is equal to 1, and that's going to be this line right here. And then last but not least, y is equal to x squared plus 1. So it goes up 1 like so, and then it does a parabola like so. All right, so this is going to be y is equal to x squared plus 1. So do you guys see the region that I have right here? Let me erase that red line here. So you guys get the idea. So that's all right there. So here's the region that's formed right here. But see, this is the part that's a little bit annoying. I'm not going to rotate this about the x-axis. I'm not going to take this thing and spin it this way. Right? I'm not going to take this thing and spin it this way, which, by the way, wouldn't be that hard, wouldn't it? It would just be the integral from 0 to 1 of pi times this function in red squared, right? Because that's what that would be if I was just calculating it that way. But they're not asking us to spin it that way. They're asking us to spin it about the y-axis. So they're asking us to take this and spin it this way, like so. Now, here's the thing. Right here from zero, now take a look here now. So you have to tilt your head now, right? So now we're going to be doing integrals with respect to y, because I'm going to be going this way. I'm going to be going across the the y-axis instead of the x-axis. Now, you might have noticed this is the 2 integral case as the label is put there, and that's because I need to do this integral twice, right? If you guys look closely, if I spin this right here, this disk that's formed right here is going to be constant from this y value all the way up to here. You see that? This disk method will be like this all the way up to here, won't it? Oh, sorry. You guys see it? Hopefully you do. Right? Because this one is pretty consistent all the way from here to here. But this one right here, this one's a little bit more tricky, isn't it? I need this from here to here. So if I do this integral with respect to y and I just do this all the way, it'll give me this big chunk right there. But I don't want that big chunk, right? I don't want that big chunk. That big chunk is going to go something like this, by the way, right? I just want the little chunk in there. So I want this part right here to get that area. So to get that volume right there, I need to do something a little bit different. So let's call this volume right here. Let's call this volume volume 1, and let's call this volume right here. Let's call this volume 2. Okay. Volume 2, that's a pretty straightforward one. Volume 2, I hope you guys can see it. To calculate that volume, right, is going to be the integral from 0 to whatever this is, and that right there is going to be 1. So it's going to go from 0 to 1, right, for this block right here, right, from 0 to 1. And the height of this, the radius right here, going from the y-axis all the way out to here, is just going to equal to 1. Do you guys see that? It's only equal to 1 because this radius right here is this radius right here that goes out to here, which is just equal to 1. And I'm doing this with respect to y. That's it. That's all that is, right? So to calculate, oh, whoops, that's, hold up. I'm getting ahead of myself. So this r, let's call this r2 right here. This r2 is equal to 1. So the area of this thing, of this circle that's going to be made right here, this area right here is going to be equal to pi times 1 squared, right? So that's what I'm going to put in here, pi times 1 squared dy. So when I calculate this one real quick, right, this is going to be equal to pi times 1 squared, which is just 1. So that's going to be pi times y, but evaluated from 0 to 1. So that volume real quick of that little piece right here is going to equal to pretty much just pi, right? 1 minus 0 is just 1. So the volume of this shape right here that's being rotated around here to here is just equal to pi, right? Now this is the part that's going to get a little bit annoying. This upper circle up here. So for that one, that radius right here, this radius right here is not equal to 1. It's not equal to 1. I don't know if you guys can see it. Right? It starts off with 1, right? The radius 1 right there, this little part right here. It starts off at that. It's not just 1 though, okay? It's equal to 1. What do you guys think? 1 is this part right here. That 1 I'm going to write right there. This right here is 1. But I don't want it to go all the way to the y-axis. I want it to stop here. So what is this chunk right here that I need to take away from that? This piece right here that needs to be subtracted. Yeah, that's a 1, sorry. Right? So that radius right there needs to be subtracted, and that thing that needs to subtract from it is this piece right here, and that's this function right here. This is y is equal to x squared plus 1. In other words, though, I need this in terms of y, right? So x squared is equal to y minus 1, so x is equal to the square root of y minus 1. So this distance right here, from here to here, right, is this function right there. So if I want to find out that distance that this is such a messy drawing, right? My apologies here, but let me draw this. Let me draw this a little bit better. So this right here, right, with this blue line down here, I'm trying to find out what this distance is from here to here, right? I know that the blue line goes from here all the way to there. I know this red line goes from here to here. So to find out what this distance is that's in purple, I have to subtract the blue line from the red line. That's all I'm doing here. So the blue line is y is equal to 1, right? I'm sorry, the blue line is x is equal to, is just this equation equal to 1 right there. I'm going to go ahead and subtract that, right, from this red line being this function right here, right? And that function right there is x is equal to the square root of y minus 1. So the radius that that's in question right here is pretty much the square root of y minus 1. Okay? Does that kind of make sense, or does that not make any sense at all? Have I lost you guys right there? Maybe it doesn't make that much sense if I write it this way. Here. So you guys can picture that this is a little disc right here, right? That's being formed. Looks like coins because it makes sense. Oh my God, David. Okay, so check this out. So picture right here, right? The blue circle that goes all the way around like this, right? That's the blue disc. If you look at it head on, right, it looks like this with radius equaling to 1, right? To calculate the area of this thing, it's just equal to pi times 1 squared. That's going to give me the whole area of this blue thing right here. I don't want that whole area. I want it with this hole in there that's missing. And that hole is this radius right here but this radius right here, this r, is equal to the square root of y minus 1, right? So that thing varies along the way. So this area right here is going to equal to pi times the square root of y minus 1 squared. So to get this area, I need to subtract the blue area from the red area. Does that make sense? If I take this piece right here and I subtract it from this piece in here, the area that I'm going to result with is this area that's this little piece right here, which is what I want, right? Which is what I want. I want that piece to be rotated around. So what I need to do is subtract the larger area, which is this one in blue, from the smaller area, which is this one in red, right? So my area function, right? My area function of this thing is going to equal to pi times 1 squared minus pi times the square root of y minus 1 squared. Can you guys see that? That's all I'm doing here. I'm looking at the bigger area that's formed by the blue and the smaller area that's formed by the red, and I'm subtracting the two. That's going to give me the cross section, right, of that circle right there. It has that this part in red right here that's going to be taken out from the bigger area that's in blue, because that's what's going on in this picture right here, this horribly drawn picture. So I'm very sorry. I apologize if it's kind of ugly and confusing, but right from here to here, right, this disk right here, if I had just taken this whole thing with it equaling to 1, it would be too big. So I need to take out the smaller area right there. And that's kind of what's going on there. So I don't know if you guys can see that a little bit better now, but I do apologize. My drawing is not that great for this one. But yeah, so to calculate this volume, right, so let's call that V1. V1 is going to equal to the integral, right, from this time, though, this is going to go from 1 to wherever this is crossing. I'm supposed to figure that out. I believe it's crossing at 2, right? I believe it's crossing at 2, right? And the area that I'm calculating here is going to be pi times 1 squared minus pi times the square root of y minus 1 squared dy. So that's the integral that I need to do there. Brian, you say you can see it now. I hope everyone else can see it as well. It's kind of weird, but it's the same idea of looking at the area of that circle, right? But you have a hole that you're taking out of it, right? You have a hole that you're taking out of it. This hole that's in red right here, that's supposed to be a hole. Hey, that looks better. Yeah, there you go. So I'm taking out that hole that's right there. And that's kind of what I'm doing here. And then this right here will give me that area of that little disk with a hole in it. If there was only a better name that we can call it, this disk with a hole in it. We do have a better name for it, but we'll talk about that later. So now I'm supposed to do this integral right here, right? So I had to split this up into 2 integrals because, like I said, the first part of it from here to here is a nice integral. There's no hole with it when I do this disk. I just take that whole volume right there. When I come up to here, though, there's going to be like a bowl shaped thing right there with that little hole that's missing in here. So I have to do that little bit of calculations, and hopefully that made sense with what I wrote out. I'm going to go ahead and simplify this out a little bit. There's a pi in both terms right here. Actually, you know what? I'll just rewrite this. This is going to be 1 to 2 of the integral of pi minus pi times y minus 1 dy, right? They both have a pi term in there. I could factor out that pi term, so I don't have to deal with that. So I can rewrite this as the integral from 1. I can put the pi out in front, and this is going to be the integral from 1 minus y minus 1 dy. Distribute that minus sign. I end up with the integral of pi from 1 to 2 of 1 minus y plus 1, so it'll be y plus 2 dy, which will be a little bit easier to do the integral of. Wait, negative y minus 2. Double check your math, knock me. Negative y plus 1, so it'll be negative y plus 2. There we go. Little mistakes along the way, knock me, that's going to cost you. So doing this integral, it's going to be pi times negative y squared over 2 plus 2y. Evaluate that from 1 to 2. Where did the 2 come from? This becomes, if you distribute that negative sign, this becomes 1 minus y plus 1. 1 plus 1, that's where that 2 comes from. Or are you talking about the 2 that's in the integral? Because I didn't show that one either. Yeah, but that's where the plus 2 comes from. The 2 from the integral was where these two lines intersect. They intersect right here at this value right here. That value happens to be 2. And that's why the integral is going from 1 to 2. It's technically supposed to show that. I'm supposed to show when does this thing equal to x equals to 1. So you plug in 1 and you're supposed to solve for it. Oh, you can plug it in here, actually. X equals 1, so 1 squared plus 1 is equal to 2. So that's where that crosses there. But yeah, that's that one right there. Let's finish off this problem. This is going to equal to pi times -2 squared. Be careful with the signs on this one. Over 2 plus 2 times 2 minus -1 squared over 2 plus 2 times 1. Simplify this out. This is going to be pi times -4 over 2, which is going to be 2, plus 4 minus -1/2 plus 2. Just combine like terms here. We got what we got. -2 plus 4 is going to be 2. Plus 1/2 minus 2. All that work for the 2's to cancel out. This volume right here that I'm calculating is just going to equal to 1/2 pi. Oh, by the way, this is volume of the. Is it the first one? No, it's the first one. Volume of the first one. So I found the volume of the first one. All I have to do now is add it to the volume of the second one. So the total volume, right? Total volume is equal to 1/2 pi plus what we got earlier with the easier one, which was pi, which means the total volume is just equal to 3 over 2 pi. That's that volume right there. So that website I gave you earlier is nice to rotate, to give you the circle around the x-axis, but when it grows around the y-axis, it gets a little bit stranger. Oh God, that's a lot that's there. Hopefully you guys can see that. I'll zoom in a little bit so you guys can see that a little bit better. While you're doing that, I'm going to get you, let me see if I can find a website that talks about the disk method and the washer method. That's what that's called, by the way. When you have a hole in your disk, it becomes this thing called a washer, which is, if you guys ever worked with like different screws and bolts, a washer is just like a metal ring, right, for your screws to fit into certain spots. Give me a second here. Let me see if I can find one. Ah, yes. This, all right. We'll try this site. You guys got that down? I want to show you this before you go. And it looks like I did not finish the last part, which is the revolving around other axes, but that's okay. We'll do that next time, along with like a more practice with the washer method. And then we're going to start reviewing for your tests next week. So we're going to be looking at some AP questions next week together. We'll be working as many as we can, and just double checking while you guys are copying this down. No one signed up for after school tutoring yesterday, which is fine. So hopefully you guys are studying and reviewing for your AP exam yourself, but I'm going to double check for today and just verify with you guys if anyone's coming today. If no one's going today, I'm not going to drive on to campus, but let's see. Double checking right now. Looks like no one signed up, so you guys got until like 12:30 to figure out if you guys want to be on campus or not. If no one signs up, I just won't show up. But hopefully you guys are studying for your AP exam and you started looking at your extra credit opportunities, aside from the the early morning ones. But hopefully you guys got this down. I want to show you this real quick. This is a simple one that someone programmed, because you can only type in one function. It looks like you can't type in multiple functions. Yeah, it looks like you can only type in one function. But check this out. Let's take a look here. All right, can you guys see this okay? So this is the function if it was x squared, and if you rotate it about the x-axis, right? This is kind of what's happening here. You're kind of taking it and you're rotating it around like so. You see it? So it makes that disk right there. But you can't see the smaller chunks of it because they kind of just do the whole thing there. See it? So that's around the x-axis. Now, if you're rotating about the y-axis, right? The y-axis, and let's say the the bound is going to go from 0 to, let's say, 2, like so, right? There it is. The equation is this one right here. If I took this one and I spun this around the y-axis, it would look like that. You see it? You guys picture that right there? So it's taking that function and it's just spinning it around the y-axis. See it? Boom. And that's kind of what we did right now, except we did it for a specific interval from like 1 to 2. See that? So we did only a small chunk of it. Man, that's some pretty cool stuff. But yeah, what we just talked about though is like a piece of it missing or a chunk of it missing. So we need to kind of figure out, hey, what the heck is happening there when you have a chunk of it missing, and why it's called the washer method. Okay, so that's the next thing that we're gonna. That's the last thing actually, which is the washer method. But it's pretty much what you guys have seen. You take the outer area and subtract the inner area, and then you do the integral of that. And that's what basically the washer method is. And that's the last part that we need to get to. But before I wrap up today, a couple things I wanted to talk to you guys about, which is your extra credit opportunity, which all is going to lock before your AP exam. Like at 11:59 the night before your AP exam, all your extra credit opportunities are going to lock out. So I wanted to bring this up before I get a bunch of students coming at me at June 8th, seeing what they can do about their grades, because at that point, it's going to be a little too late. All your extra credit opportunities are up and running now. They are pretty much for you to get to. So I didn't put the link for the Calc Medic there, but there's still extra credit there for you. There's still extra credit for you on the College Board. There's still extra credit for you on the Khan Academy, and there's still extra credit for you on the early morning problems. So here's what I want from you. Do these extra credit problems before May 24th. Your AP exam is on May 24th. All these extra credit things lock on May 23rd. Don't wait until the last weekend to do all of this. It's a lot of stuff. Do like a little bit each day. I've been doing these early morning ones just to get you ones that you can easily earn for like, 30 minutes. I messed up today though, so I'll make that up for you. But for the College Board one, each of these videos are about an hour long, and they cover every single topic from Unit 1 all the way up to the exam on different days. They don't go in order. They just go in what they think is important. So that's why the first video you watch, if you look at day 1, they believe derivatives and chain rules are important. They spent that whole time talking about that. All you got to do is do the problems with them and practice along the way. So that's extra credit that you can earn right there. The other extra credit that you can earn is the Khan Academy stuff. Go to Khan Academy. I've assigned every single unit on there, and I'm going to be focusing mostly on unit tests that they have on there. Those are assigned, and the quizzes that they have along the way. I'll also be looking at how many videos you watch as well on top of that, but that will be a smaller portion of it. It's not worth as much as doing the problems on there. So all of these should be assigned to you already, and I should be able to see how you guys are doing, right? Yeah, so looks like one of you guys have completed quite a few of these. No one's completed these yet, but that's perfectly fine. So that's another method of extra credit that you can get. And the last one is Calc Medic. I haven't put the link up on there yet, which I should, but most of you guys have joined Calc Medic. This one's the same thing. It just breaks down from Unit 1 all the way to this. It's pretty much like Khan Academy. But they have video of a different person explaining it, and they also have other practice problems for you to do in there. So you can go into here for the derivatives. You can do the multiple choice. And what I love about this site is the free response questions have the solutions, and you can practice grading them. And we'll do that together as well for other problems. How much is the College Board extra credit worth? Each day is worth a different amount. No, each day is worth, I wanted to say about, I want to say 5 points just to make it a total of 40 points, but then that's a lot. That's a lot. So I might bring it down to 4 points for each day to make it down to 32. I might make it down to 32 total extra credit points. I think that's going to be a little bit more reasonable because 40 is like a big chunk of a test. Actually, I don't know if it's actually worth the test. I think I might have put into your quiz extra credit or your homework extra credit. I need to go check on that. So each one is on different sections there. But yeah, I'm bringing this up right now because I guarantee you there's some of you who are going to come at me to ask about something that I can do for your grade. And I'm going to say right now, this is something you can do for your grade, right? If I see you have this extra credit and you've attempted these extra credits and, We take that last test after the AP exam, which, by the way, you're going to have a test after the AP exam, but don't think about that too much right now. This extra credit will help you towards that. All right. And I saw that you complete this extra credit and you get a score and you're like, oh, crud. You shouldn't have a D in the class is what I'm saying. If you do this extra credit, you shouldn't have anything lower than a C. Even if you bomb my tests, it's not possible. So if I see that you're coming at me for some talks with your grades, you better make sure that you've completed at least some of these extra credit problems in the morning, Khan Academy, College Board, or Calc Medic. Because if you haven't, and then you come ask me for stuff after the AP exam, I probably will just ignore your pleas. You know what I mean? So if you have these done, you know, awesome, good job, keep going with it. If you haven't started them, I'm not yelling at you to start them. I'm just asking you nicely, like, hey, you still have a week and a half. You can start just by one easy thing, just by going over here. I kid you not. This day one, the problems that I'm asking you to do, right, looks like it's a lot. It's this worksheet right here. Let me see here. This is worksheet right here, and it looks daunting. There's like 3 pages, 4 pages, and it's like, crud, I got to do all this for extra credit. The video, the people in the video actually work through these problems. Can somebody actually help me out here? Like, how many problems do they leave you to do on your own? Does anybody know? Has anyone done this first one yet? I believe they worked through quite a few of them with you, but I could be wrong. But I believe that you only have to do like maybe like 4 problems or so on your own, 5 or 6. Yeah, and I think it's not that bad. You can just follow along with them and get the answers from them, and then do the rest on your own just to try it. And then that's it. You hit submit, and you get your extra credit. Anyways, long-winded talk about points because I know some of you guys might be worried about your grades. And I want you to just think about this right now. Like, you shouldn't have to worry about your grades. Do these extra credit things. I pretty much guarantee that you shouldn't get anything lower than a C in my class, as long as you do all of them and you do them honestly. Anyways, that's going to be it for me today. I know it was a long-winded talk about this at the end of it, but I needed to get that out there because I know that some people need to hear it. But yeah. Anyways, that's it, guys. It's 10:37. Have a good rest of your week. Sign up for after school tutoring if you want to stop by today or tomorrow. I have office hours from 2 to 3 today, though. So other than that, have a good rest of your day, everybody. So long. Farewell. Bye, everyone. Where do you find the Khan Academy? So bye, Ava. Bye, Monica. Sam, to find the Khan Academy, on the home page, go on to the extra credit options right here. Click here for extra credit and click on the Khan Academy right here. And oh, shoot, it doesn't have the code for you to join. Give me 1 second. Here it is. The class code is right here, Sam, if you want to join my Khan Academy class if you haven't done so already. It doesn't look like you have. So let me put that in the chat, Sam, if you're still there. Yes, you are. So there's the Khan Academy code. Use that to join my class on Khan Academy. I'll go put that up in the page right here as well. Okay. But yeah. Let's do that right there. All right, everybody else, I'll see you guys later. Have a good rest of your day. Oh, I forgot to stop my recording.